Thank you very much, Dan. I hope you're seeing the right screen.
Looks good.
All right. Well, it's a pleasure to present here today. What you'll hear from me is a perspective from a company that's working in accelerating genetic improvement in dairy and beef cattle. I think we probably got a spot in this workshop because STgenetics has been a very forward-thinking, technology-driven company. So I would like to give you a little bit of a background about our company, a little bit on the industry and how genetic improvement is currently performed, and then provide you our perspective on the status of gene editing technologies as they apply to cattle genetic improvement. So it all starts with our commitment to really address this massive challenge that requires us to produce more quality food for a growing population, do that with reduced available resources, and all of this while reducing the environmental impact of our industry production practices. So to meet this challenge, we're convinced that the answer is to improve efficiencies of animal production, and the solution is to use technologies to achieve that. So as a goal within the company, we always describe it as achieving a sustainable future utilizing biotechnologies, bioinformatics, biosensors, right, to improve efficiencies in livestock production. I want to have make a pause here in terms of the word sustainable and how we use that as a very broad concept, but really we obviously mean with this environmental sustainability so that this practice can continue for future generations, but also a sustainable production system, sustainable supply chain, sustainable business, and kind of a sustainable way of life for both our producers, the markets and the consumers. So as a company, I mean, this slide summarizes some of the technologies that we're currently utilizing to support our goal. These obviously include sex sorting services. ST provides services to multiple leading companies in genetic suppliers. We have labs in 25 different countries. Genomics and reproduction are used to identify genes influencing beneficial traits and then accelerate the dissemination and the genetic improvement on those traits. We have a company that provides genomic testing services as well. And we use bioinformatics and biosensors to monitor and provide traceability for animal health and animal production efficiencies that, again, combined with genomics and reproduction and sex sorting services, lead to genetic improvements that can then be provided to farmers and to the field to improve the outputs and the yields of the production populations. And we still don't have gene editing as part of our toolbox yet, but we strongly recognize the great potential that these approaches and these technologies could have in delivering improved genetics. I also wanted to share this timeline of the company because I sometimes get the feeling that this STgenetics is probably not a very well-known company, but this timeline really highlights the commitment that STgenetics has put into developing and delivering advanced technologies. So it sort of all started with in 2002 when the company licensed sperm sorting technologies. Soon after, in 2007, ended up acquiring the company holding the IP for sex sorting and XY Inc., and combined that with IP from Monsanto, as well as acquiring Cytonome, an engineering company located in Massachusetts, was working on microfluidics and flow cytometry technologies. And with this investment and over the years, this led to an improvement in sex sorting efficiency that have multiplied by tenfold what was the original technology. So more recently, this year, we're rolling out these SuperGen sorters that are fully automated machines that have, again, an output 10 times better than the original technology that was acquired by the company. At the same time, and in parallel to these engineering advances, ST continuously work on improving process of sex-sorted semen. And so with releases of Sex Ultra for million products, high purity products, and more recently Ultra Plus products, the fertility of sex semen has now reached a point that's very close to the fertility of conventional semen, to the point that in many countries, the production of replacement Holstein or Jersey animals for future commercial populations are almost exclusively done with sex-sorted semen. Now, I also wanted to highlight from these slides that in 2015, ST launched its own genetic line in the US, later acquired companies in Europe like Cogen and Inseme to have a more wide distribution of genetics, but started a very intensive genetic improvement program. And after 9 years of this genetic development program within the company, as of last week, for example, there was the national US proof for dairy cattle. So ST ended up having 52 of the top 100 bulls based on the net merit dollar ranking, based on their genomic predictions. And this includes also some unique characteristics like pork carrier animals that are currently ranking at the top 33, basically in that rank. So that would be within the 1 or 2 percentile of the breed. Now, if we talk about genetic improvement, it's always important to, keep in mind this equation that was recently presented by one of the fish session presenters. But this breeder equation that sort of translated to my understanding is that, right, the speed at which we make progress in genetics is directly related to the accuracy of selection, variability in the population, the selection intensity that we apply to that program, and it's all indirectly related to generational interval. And generational interval becomes very important when we talk about cows because of their long biological generations. And some of the technologies that we apply to speed up this genetic progress clearly include genomic technologies that allow us to more accurately select animals for the next generation, reproductive technologies that help us reduce both generational intervals, but also increase the selection intensity. For example, with the use of artificial insemination, a single male can breed 40, 50,000 animals in a year compared to maybe a couple hundred in a natural service situation. And then the combination of genomics and reproductive technologies allow us to shorten those generational intervals. So instead of 5 or 7 years, as it used to be a reasonable generational interval for genetic improvement in dairy cattle, we're now closer to 2.5 years on the male side, and maybe even less than 1 year if we introduce advanced in vitro fertilization technologies for the female side. Now, when we consider gene editing or any other intentional genetic alteration, that is a great way of both introducing new genetic variation and also helping reduce some generational intervals as a way of speeding up how we introgress new variants into already advanced genetic populations. So using conventional methods of genetic advance, we have seen that with widespread use of artificial insemination, maybe strategic use of embryo transfer and in vitro fertilization, and intensive use of genomics, the productivity of dairy cattle this data from the US has continuously improved to a pace of about 10% improvement over the last 10 years. And if we continue this improvement, certainly this is going to help us meet those goals. However, it may not be enough. Now, what we are seeing on the genetic side, so part of this improvement may be because of improvements in nutrition or management or reproduction, but certainly from a purely genetic point of view, we do see a significant improvement over the years, especially after the introduction of genomics in 2009. We have seen that the pace of this genetic improvement in dairy cattle has doubled and continues to accelerate, not just linearly increase. So if we look at this bar graph here, and we consider that last bar to relatively represent the current maybe production population, and this is expressed in an index that's used for breeding called net merit dollar, and it's supposed to represent the profit for an animal with certain genetics over the lifetime of that individual. So we're sitting about 100, 150 on average for the production population in the US. But today's bull populations, if we look at the top 10% of bulls, with an average of 1,100 net merit dollars, if we were to use exclusively those bulls, breed every cow, generate a replacement for the following generation, and only milk that new generation, that would result in a 40% increase in profits, and those profits come mostly from increased productivity for the dairy herd. If we go a little bit to a further extreme and only use the top 1% of bulls, that would be an over 50% productivity improvement. Now, this doesn't happen. So the technology is there. The bulls are there. 10% of bulls, we're talking about 700 bulls times 50,000 straws each animal. We can provide semen for the whole population. I'm not talking about my company, the company I work for. I'm talking about globally as genetic companies. But it doesn't happen. And I wonder why is that? And I think that's explained by industry dynamics or breeding program limitations and logistical constraints, but also cost of implementing these technologies in such a wide form. So what I want to drive with this is the idea that we have technologies today that could drastically improve productivity. But given the low generational intervals that we experience with cattle, the slow replacement rate of the productive herd, I think that there is a need for accelerating this improvement and to provide better solutions, I'll say, to the dissemination of these improvements. So coming to gene editing, and I want to give you, as I said, our perspective from the point of view of a company that looks very closely to innovative technologies as a way of delivering those efficiency gains needed to meet this food challenge, right? So we see gene editing as a very promising and exciting technology, especially contributing to that in genetic variation. Now, from a technical point of view, and maybe taking also from my experience while working at UC Davis, we're convinced that the technology is to a point that we can modify any sequence in the genome of a cow, or to that matter, in any animal where we can manipulate embryos or do cloning and do cell cultures. So we can do that efficiently, we can do that precisely. One of the important considerations is what to modify, right? And we've seen some really good examples in previous talks. So we can remove allergens, we can make animals more thermal tolerant, we can remove unwanted developments like horns using pole genes, increase yield and quantity of products through, for example, myostatin knockouts, maybe introduce omega-3 fatty acids for higher health. Disease resistance or disease tolerance is a big aspect that tends to have low heritability for conventional genetics that, if identified and introduced through gene editing, could have a significant impact on production systems. And we could potentially skew sex ratios. So we currently do that through sperm sex sorting that requires to separate male and female sperm individually one at a time. Not very efficient, I'll say, although effective. So if we could do that through gene editing, why not? That certainly has an impact on our production systems. So we think that this aspect of the gene editing technology has been solved. Now, where we see some challenges are more on this aspect of the regulatory system, right? So we on this workshop discussing how should we approach the regulatory system. There is a regulatory system in place, at least in the US and in many other countries as well. From a company point of view, the system is very cumbersome, it's very time-consuming, and at the end of the day, very expensive. So some of the examples that we have been discussing that include intentional genetic modifications that have been approved by the USDA, FDA for human consumption include the aqua bounty salmon, and that's a high-growth fish, depending where you get information, but some information shared at some point by the company indicates it took 23 years to get approval and maybe over $120 million in investment to go through that barrier. Of course, they were the first one. This was a full transgenic technology using genes from other species. Other examples include the alpha-gal knockout pigs. We heard about those yesterday. This is removing an allergen from pork, which allows people with red meat allergy to enjoy the flavors of animal products. So we don't know what the process caused, but it's a byproduct of a medical application. So I'll say it's probably subsidized by that industry to some extent. We know some animals were approved for consumption as requested under an experimental approval for nanos 2 knockout pigs. Those are animals that lack germ cells. So the Washington State University indicated that it cost them kind of $250,000 to have a few animals approved so that they can enjoy some gene-edited sausage, and everybody was okay. No bad effects from that. And finally, we just heard from Todd about the sleek cattle that have increased thermotolerance. This is also a naturally occurring mutation. The FDA has granted them enforcement discretion, meaning these animals can be commercialized and their products can enter the food chain. But clearly, for developing new products, it's a steep barrier to surmount when we want to introduce novel traits. Maybe not as steep if we want to work with naturally occurring mutations that can also be introduced through standard breeding approaches. Now, I'd say the aspect that has limited STgenetics from entering these exciting technologies and trying to develop these technologies for distributing to the market is the potential controversial aspects of market acceptance and maybe a sufficient competitive advantage. And the main example that we can use to illustrate this, why we feel that there may be possibilities to make this controversial and that there could be some pushback possible, come from the experience with recombinant bovine somatotropin. So this is another recombinant DNA technology, not used to modify an animal, but actually to produce a hormone that used in cattle increases production efficiencies, decreases greenhouse gas impact of meat production, but when introduced to the market, had some I'll say, reaction from that market that led to some commercial outlets starting to label milk coming from animals not treated with this hormone as RBST-free milk. And they put this disclaimer that all the science and the FDA have determined that there is no risk consuming milk from BST-treated cows because the milk is virtually, actually, indistinguishable from milk from cows not treated with RBST. However, the tiny label that said RBST-free milk led to the disappearance, at least in US grocery stores, of milk not labeled that way. That meant that milk processors started to incentivize milk producers not to use RBST, initially by providing financial incentives. Eventually, the product disappeared from the production system, or almost disappeared, and the incentives disappear as well, but the market grew in this situation of not using this product, just to prevent the possibility that the consumer would choose not to consume it, right? So the big question for us, and I think for a lot of actors in the industry, is what will the producer or the consumer do when faced with this choice? Maybe a milk jar labeled from gene-edited cows and a milk jar labeled with nothing. Or maybe the other way, right? A milk jar that's not labeled and may come from gene-edited cows, and a milk jar that's labeled GMO-free or any terminology you want to use, but milk from cows without intentional genetic modification. And until this question is answered at the marketplace, the introduction of gene-edited products in this production system becomes highly risky. So some of the considerations that we look at when contemplating the use of gene editing in production of cattle products are, well, what are going to be the benefits and risks of the edit or of the modification for the genetic company, for the producer, for the processor, for the retailer, and finally, but most importantly, for the consumer. Are we going to be able to provide a trait that the consumer is going to seek for? Therefore, that milk jar label GMO or gene edited will be more valuable, or is that going to create that perceived risk and become less valuable? As we have been discussing, I think, in this workshop, traits that provide a direct benefit to the consumer are definitely more likely to achieve acceptance and not to generate these negative perceptions. Probably this will happen initially at niche markets, and maybe that is a great place to start these experiments and answer this big question: how will the market react? The long generational intervals in cattle certainly increases this uncertainty of the investment. It takes, about 30 months, so 2.5 years, for an animal that's bred to a gene-edited semen, let's say, or put a gene-edited embryo, to find its way into the marketplace in the case of dairy cows, or almost 2 years for that in the case of a meat-producing animal. And these are very high value and costly animals to raise, so they require significant investment. On top of that, if we expect any product differentiation and transparency in labeling, that will require traceability and segregation of those animals, not only during the production, but also processing and commercialization, which is likely to add cost to these novel products. And once we introduce a genetic change, it's not easily reversed. So it's not like we can stop administering or take it away from the animals on the ground, such as was the case with the bovine recombinant bovine somatotropin. So with all this said, the trait that is going to be introduced will have to provide a significant value margin to justify all of these time risk, expense risk, and basically this difficulty in turning back or removing these products in case that's needed. Furthermore, in case of global companies, and I would say the global genetic improvement programs, if we consider that export and import markets and the flow of genetics around the world, this will require that a coordinated global approach is used to both regulations and market acceptance for more companies that are in this, let's say, global genetic business can jump and introduce genetic advanced concepts that use gene editing or other intentional genetic modifications. So this is, like I said, this is the perspective from our company, from STgenetics, and I leave you with this sort of traffic light snapshot that we have, where the technology, like we think, is more than okay. Regulations certainly need more work, and we appreciate this workshop helping with that. But we are still asking these questions, and we would really appreciate answers to what is the market, how the market is going to respond and accept this type of product, not only from the consumers, but also retailers, processors, and producers, and so on. And thank you very much for your patience, and look forward to answering some questions during the question Q&A session.